This is the audio notes on how different acids and bases have different strengths and how that relates to equilibrium. So I'm going to show you my first slide. Again, the first bullet point, there's a difference between a strong acid and a weak acid. A strong acid completely dissociates in water, completely donates that H plus to make hydronium ion. You can see at the second bullet point, HCl is an example of a strong acid. So it reacting with water to make hydronium and chloride ion. A weak acid, however, only partially makes hydronium. Notice the double arrow that I drew in order to show that. This is acetic acid plus water, making some hydronium and some acetate. And some of it stays as a reactant. Today you'll be going over several different things associated with strength. The Pogel packet will help you to identify a weak acid from a strong acid, hopefully. But to start off with just the definition, it's whether or not you can completely make the hydronium or only partially. Bases, same sort of thing. Sodium hydroxide is a strong base. When placed in water, since it's an ionic compound, it breaks up into its ions completely. Therefore, when we go back to the pH calculations that we did last class, if you know the concentration of sodium hydroxide, you know the concentration of just the hydroxide. A weak base similarly doesn't completely do it. Most commonly, you're going to see all non-metals involved with something like this. An example could be ammonium hydroxide, only partially makes the ammonium and the hydroxide ion. So the simplest way to identify is a single arrow versus the double arrow when determining that. If you look at the equation, again, if you are not given an equation, if you're just given an acid, for example, hopefully the Pogel packet that you work on later today will help show you how to identify some acids being strong and others not. If it is a stronger acid, more products are formed. Again, just think about that equilibrium expression. If it's a single arrow to the right, it's fully creating the acid ions versus only partially if it's a double arrow. A couple pages in your book will show equilibrium constants for these things. Starting next class, we're going to do calculations dealing with equilibrium constants and the dissociation of acids. And we'll go back to our ice tables and all that fun stuff too. Last thing to bring up, when talking about acids and bases and how they dissolve, especially when we define an acid with dissolving in water, we often have to refer to conjugate pairs. Conjugate pairs is vocabulary that you do have to be familiar with, not only as we talk about this difference between strong and weak, but when we get into solutions called buffer solutions, conjugate pairs are often brought up at that point too. So it's something that we're going to practice the identification for here in a little bit. If you have an acid, after it lost a proton, on the other side of the equation, you would have its conjugate base. The conjugate acid is the product of a base gaining a proton. Let's give you an example with a weak acid, hydrofluoric acid. And if you're not aware that hydrofluoric acid is weak, again, the Pogel packet will bring up this specific example in a little bit. I'd be able to identify, looking at these two reactants, that HF is an acid. Granted, water has behavior of acid and behavior of a base. HF is more acidic than water, so it's the one that's going to act like an acid here. An acid loses its hydrogen, its H+. And in doing so, here's what's left over from that HF, the F-. So HF and F- are conjugate pairs of one another. This is the acid, this is its conjugate base. In a similar method, H2O in this equation, since it's accepting a proton, it's acting as a base. This hydronium ion then is the conjugate acid of that base. So these two are conjugate pairs, and these two are conjugate pairs. So labeling acid versus base is part of what we want to do but really it's the HF and the F minus that are pairs of one another. An acid and its conjugate base. Again, first bullet point, conjugate base is the product of the acid that remains after losing a proton. Conjugate acid is the product of the base after gaining a proton. This base gained a proton. That's why these two are conjugate pairs of one another. Again, it might seem kind of silly identification, but this vocabulary is used in later work that we do, so you do need to be aware of this, and that's what you're probably going to start practicing right now with a sheet that you picked up on the way in.